everyone, and welcome to our third ALG-AD webinar. If you missed our first two webinars, you can watch the replay on our YouTube channel, and link to these webinars will be appearing in our chat box. Today, we will be going to Belgium to talk about microalgae cultivation and photobioreactors. We will go to the Oostkamp near Ghent to discover a pilot site where we cultivate consortium of algae chlorella and desmodesmos in photobioreactors as part of the ALG-AD project. To talk about the work carried out on this pilot site, we welcome Marcella Fernandes de Souza, project manager at University of Ghent, coordinating the research line and new biomass of which ALG-AD take parts. Marcella holds PhD in technology of chemical and biochemical processes, and one of her current research interests is using microalgae for remediation of agri-food wastewaters. During her presentation, you can ask your question and at any time and put them in a Zoom chat box. We will have time specifically dedicated to answer your questions after the presentation. Thank you for your attention and have a great webinar.
Good morning. My name is Marcella Souza. I'm a project manager at Ghent University, and one of the projects I'm working on is the ALG-AD project. And today I'll be talking about the results we gathered in the project about growing microalgae on plant-based digestate, the Belgian pilot site. So this pilot site is being operated by both InnoLab, which is an AD consultancy agency, and Ghent University, where I work. So I just want to start with a brief introduction on the ALG-AD project, where we propose a circular solution for the nutrient surplus challenge in Northwest Europe. So Northwest Europe is a very densely populated area with high amount of activities of agriculture and animal husbandry. And these activities generate a lot of waste, which is organic waste, that can be processed through anaerobic digestion into two streams, so biogas, which will be used for production of energy and heat, and digestate, which is the focus of this project. So digestate is a nutrient-rich stream that is currently being used as fertilizer. However, due to nutrient surplus problems, as I mentioned in the beginning, you have in Northwest Europe several areas where the soil is so rich in nutrients that if you apply too much, it will run off to water bodies and cause eutrophication problems. So what we want to do with this project is to use this surplus digestate that cannot be applied to the land as a nutrient source for microalgae cultivation. Then, once we have the biomass grown on digestate, which is protein rich, we process it into animal feed. And in that way, we can create a circular solution for this nutrient surplus in Northwest Europe. However, using digestate for growing algae, it's not a simple process, and it has a lot of challenges. And this can be summarized in four main challenges, which are suspended particles, high viscosity, dark color, and high ammonium concentration. And for the dark color, I have an example here in the picture. So you can see that even when digestate is diluted at 20%, it's still very dark. So only when we go to 10 or 5% concentration, which are very low, you start to see the transparency happening. So how is the Belgian pilot site dealing with these challenges? So I'll first start with the suspended particles, and for that I'll briefly explain what we do in the Belgian pilot site. So we get the liquid fraction of digestate from an AD plant in Belgium. This is further filtered in a 10 micrometer pore size filtration unit, which we call paper filtration, but actually is a cloth bag with a pore size of 10 micrometer. So this removes most of the suspended particles. And then this filtered system is fed to our reactors, which are situated at InnoLab. And this is different from the other pilot sites. So the two other pilot sites in the UK and France, they're focusing on using smaller pore size filters. So they use microfiltration and even smaller for the French pilot site. So we wanted to test how the paper filtration is comparing with a microfiltration. And this was not done in pilot scale. So this experiment was done in lab scale. And we have the green bars with the paper filter digestate at 10 micrometer pore size. And in blue, you have the microfilter digestate at 0.1 micrometer. So we compare these in different concentrations, and you can see that mainly at the lower size concentration, so 2.5 and 5% digestate concentration, the paper filter digestate gives a better growth than when using the microfilter digestate. And this result is important because, as I will show in the next slides, we are mainly using this reduced digestate concentration, so 5, 2.5 and even less. And why is paper filtration giving better results? So we have noticed that it maintains more nutrients. Of course, it has a smaller pore size. So some of the suspended particles actually remain in the digestate, and these are sources of nutrients. Also, the paper filtration, because it uses 10 micrometer, which is bigger than bacteria size, it maintains the benefic bacteria that are actually helping to make the nutrients more bioavailable for the microalgae cells. And also, on a technical economic perspective, the paper filtration has a lower energy expenditure due to its higher pore size, and so it has lower cost when compared to the other filtration units with lower pore size, smaller pore size, because there you need to apply pressure. In our paper filtration unit, gravity is the driving force for the filtration. However, it doesn't come without disadvantages. So there is a possible presence of pathogens. So the same way that it allows the good bacteria to remain in the system, it can also allow pathogens to stay in the system. However, we have tested this in the project, and this was not a cause of concern. And so paper filtration also maintains most of the color of the digestate. If you have seen the previous webinar, Florian, she presented some results with microfiltration and ultrafiltration, and there you see most color removal. And here with paper filtration, because some suspended particles still are in the system, you still have a dark color. However, this is not a problem, as I'll show in the next slides, because we dilute the stream. So, for the other three problems, the high viscosity, the dark color, and the high ammonium concentration, we deal with them basically with the same solutions, which is dilution and fed batch. And I have here a graph from the Belgian pilot site to show how this is effective. So what we have here in blue is the biomass growth, and you can see the unit in the secondary axis to the right. And in orange, you have the nitrogen concentration coming from ammonia. And this is on the primary axis to the left. So what we did was we started with around 50 milligrams per liter of ammonia, which is lower than the toxicity level, which is around 100. We let it consume. So for about 6 days, the cells were growing, the nitrogen was being consumed. Then we fed the reactor again. We let it consume again, and then for 10 days it was consuming, and then we fed it again with a higher concentration, and then again it went down for the next 10 days. And you can see if you follow the blue curve, we were able to reach exponential growth. So this means that there was no nutrient lacking in the system. The cells were growing very nicely. And at the end, we fed 5% digestate to the system, which is around 150 milligrams per liter of nitrogen coming from ammonia. And we were able to reach a final concentration of 1.7 grams per liter. So no toxicity effects were seen, not even by light penetration problems or because of ammonia toxicity. So we also have vertical system at InnoLab. So those results that I showed in the previous slide were for the horizontal reactor, but we also have a vertical reactor. So the horizontal is a commercial one by Lgem, and you will see in the next presentation more about this system. And the vertical reactor was designed by the ALG-AD team at Swansea University as a low-cost system. And so, as I showed you before, with the horizontal system, we were able to reach a final concentration of biomass of 1.7 grams per liter, and the productivity was around 0.1 grams per liter per day. When operating the vertical reactor with the exact same conditions, so similar inoculum, similar feeding strategy, we were only able to reach 0.7 grams per liter, with a productivity of 0.03 grams per liter per day. And as you can see in the slide, in the right side graph, the 0.7 was really the maximum that we could reach. We tried to operate the system for 10 more days, and there was plenty of nutrients available in the medium, and the algae did not grow. And this is mainly because, as you can see in the picture, the horizontal reactor has much larger tubes with a larger diameter than the horizontal reactor. So the lower results obtained with the vertical reactor are less because it's a vertical reactor against a horizontal reactor, and most because of the size of the tube. So with larger tubes, you get more light penetration problems, you get more self-shading by the cells, and you have a lower density that you can reach before having these light penetration problems. So just to be fair with the system, we did not operate this that much because we are getting better results with the horizontal. However, the UK team is operating the vertical reactor, and they were able to match our productivity. So they get quite high productivities with the vertical reactor. However, their concentrations are still much lower than ours, and they usually don't get more than 0.7, 0.8 grams per liter. Usually is even lower. So what are the next steps for the Belgium pilot? We want to optimize inoculum. So you see that we have modeled the system with the data that we have gathered so far. And in this graph, you see different percentages of inoculum and what the biomass production on grams per day we would get with these. So right now we are operating at around 20% inoculum. And in the graph, you see that if we go higher to 50% of inoculum, we might get higher productivities. Of course, this doesn't come without its disadvantages. So if you only renew 50% of your medium, it might be that you will get some toxic elements being accumulated in your system, which may cause the culture to crash. So we will see, and we have to find a balance between media renovation and a higher inoculum that will give us higher productivities. We also want to optimize the feeding regime. We got a good productivity, but we think that if we optimize it better and keep the nitrogen levels lower, we might be able to get even higher productivities. And most importantly, the way we did this feeding, we usually get around 20 milligrams per nitrogen, milligrams of nitrogen per liter at the end of the cultivation, which is higher than what the legislation allows for dischargeable limits. So right now we cannot discharge this water. And the idea is to get the system to also have clear water at the end that you can actually discharge. And for that, we have to optimize how much nutrients we give to the system. And finally, we want to recirculate the water, because right now, as I told you, we're using a very diluted system. So basically the whole volume of the reactor is clean water. And if we can recirculate this water after harvesting, so we take out the cells and the remaining medium, we just put it back into the reactor, we will reduce the environmental footprint of the process, which is the goal of the ALG-AD project. So thank you very much. I hope everything was clear, and if not, I'm happy to answer some questions. Thank you.
Thank you very much, Marcella, for this presentation. We will continue this webinar with our second guest speaker, Marieke Vanthoor, director of research and development part at Lgem or Synalgae, where she studies microalgal growth and application on lab, pilot, and demonstration scale. Marieke has a master in chemical engineering and in biotechnology and PhD in marine biotechnology. She will present today her company and the tubular photobioreactor technology from Lgem and Synalgae using our Belgian pilot site. As introduction, I would like to invite you to watch the short video to discover Lgem and Synalgae company. Thank you all for your attention, and remember, you can ask questions to Marieke in chat box at any time.
Hello, my name is Sander Haaswinkel. Allow me to introduce you to our newest Lgem Algae Hub. Here we can demonstrate and share a look and feel of our newest algae technologies. Lgem is able to deliver worldwide algae solutions to any scale. Our team offers expertise in planning, realization and engineering that is needed for complete and successful algae projects. The Lgem Hub delivers our customers much needed testing capacity, in our view, a must-have in any scale-up aspiration. Testing is supervised and executed by an expert team or with the customer's own operators. It's Lgem's goal to deliver the best solutions and to lower our customers' investment risk. Good preparation and assistance will give our customers the best possible start of their operation. Behind me, you can see the long-time operational and trusted Lgem systems, but then in a totally new upgrade. These systems offer some huge advantages what make them the best the industry can get. All of our systems are equipped with our proprietary bubble brush and wave wind technology. These allow our systems to operate without biofouling and at a super stable pH. Lgem systems have the lowest energy demand of any tubular photobioreactor system available. Lgem's newest generation systems are fully automated and seamlessly integrated in an up and downstream process. Integration and automation makes growing algae much more effortless. The new AI modules will aid in a much faster improvement and higher yields. Our photobioreactors range from 25 liters to 45,000 liters and can be delivered integrated in a complete project. We are ready to assist you.
Hi all, thank you so much for inviting me to give a presentation about what we do at Lgem. My name is Marieke Vanthoor and I'm Director R&D at Lgem. First I would like to explain you a bit more about our company Lgem. Many of you probably know the company Lgem already for a long time, but since last year we have merged with another Dutch company, Synalgae. And this is really done to join forces and to be able to create large-scale options with the proven technology Lgem already has for over 15 years. Synalgae consists of two major shareholders, and one is Bosman van Zaal. Bosman van Zaal is a technology provider for the greenhouse sector. They construct greenhouses and also provide all the technology and automation needed inside greenhouses. And Olij Trading is a greenhouse owner and has many years of experience with rose growing and other plants, but is now looking for new business models inside the greenhouse sector. So combining the greenhouse and large scale and automation and technology knowledge together with the algae production and system knowledge from Lgem, we are now able to provide large scale solutions for growing microalgae. Here in the picture you see all the shareholders, where also Eugène is one of them. Unfortunately, he is not able to give the presentation today, so that's why I took his place. We have as a vision to provide proven technology to make high-value photostatic microalgae production mainstream. And by mainstream, we mean that we want to be able to create large amounts of biomass for microalgae by creating the technology necessary to do this. So we want to provide our clients with proven technologies so they are able to easily make high-value microalgal biomass for the market. We think that microalgae are the natural plant-based ingredients for food, feed, and pharmaceutical applications in the future, and therefore we need to be able to produce more. And to create this high-value and economic microalgal biomass, we have developed a robust, clean, and efficient photobioreactor technology. So what do we provide? What's our service? We provide turnkey solutions to produce microalgae, and including in this turnkey solution is that we can design the whole plant for you based on space and elements that you already have. We can provide you with the seed train going to scale up your microalgae production from lab scale up to the large scale system. We provide up and downstream, so you can harvest your algae up to centrifugation, and we also provide you the nutrient tanks and mixing tanks to inoculate and also to harvest and refill your systems. We can even construct your greenhouse, as our partner is very good in doing that. All of the elements we provide are automated, and all the elements are connected. So you can have one point deciding, okay, we want to harvest an X amount, and then the new nutrients will come in. We also do recycle our nutrients after harvesting to not waste so much water. So this is what we can all provide you. And also, if you just want one small reactor for in the lab or for a pilot test, that of course is also still possible. Then let me explain you a bit more about our PBR technology. The PBR technology is risk-free, stable, and also very reliable. We have over 15 years experience in growing microalgae in our systems, and the basis is the same. It's a tubular system, glass made, and it has low operational costs and expenses, and this is due to the fact that the energy requirements are quite low, and also the operational or time input man hours is very low due to the automation. It's a smart design. You can create high quality biomass, high output, so the productivities we can reach are very high. It's a versatile system, and it's exceptional hygienic design. So you can this also relates to the quality that you can provide, because contamination issues are nihil, because we can very well clean it and keep the system closed, and it's easy to use, easy to clean, and it's all controlled, and we have smart measurements, so we can control pH by adding CO2, and it makes it all very stable. One of the key elements that we have in our tubular photobioreactors is having a two-phase system. We have both air and liquid in our system, in which, of course, in the liquid the algae are growing, but having this two-phase system has several advantages. First of all, due to the waves that are created, we get some kind of wavy wind and a bubble brush, and this makes sure that we prevent biofilm forming, because it's continuously cleaned, and also mixing is very efficient. And in the air phase, we can add CO2 when necessary, and due to to the large area between air and liquid, we have an optimal gas exchange between the two phases. So there is a very efficient use of CO2, which makes pH very stable over the full length of the reactor. And the produced oxygen is continuously exchanged to the gas phase, so there's no accumulation of dissolved oxygen and no limitation in growth, therefore. Our systems can be operated with only an air pump, We do also have a liquid pump, but it's not necessary to use it, and this means that low energy consumption is used in our reactors. So even vulnerable cells that cannot stand shear are okay to grow in our systems. Yeah, here I want to show you what we've done for the control and measurements. Several sensors or several parameters in the system are of course very essential and crucial for the process, and these include pH, temperature, water level in the tank, in the system, and also light intensity. And by measuring these parameters, we can control what we need in the system. It is also optional to get more sensors if you do want, if you need more pH sensors, or if you do want to measure CO2 level in your system. It is possible, but these are the essential sensors that you need, and which we will always provide. And by measuring this, we can control the CO2 injection based on pH, we can control the air blower based on the water level in the tank, and also in the greenhouse, for example, we can close the shading cloth if the light intensity gets too high or if the temperature gets too high. The sprinklers can go on, and heating pipes can also be used to heat up the greenhouse whenever it's getting cold in the night, for example. And all the data that we measure, we are plotting it in a dashboard, as you can see here, and the bar graph that is shown here also is a calculation behind it, so you know the total amount of light per day that the reactor received. And the total usage of CO2 per day is plotted here, so it's very easy to see what's going on, and also alarms are sent out if some failures are getting out of range. So this is all included there in our control strategy. Here you can see some of the PBR models that we have in our portfolio. It ranges from small scale to large scale systems, and this is also to be able to provide a complete seed train going from small and scaling it up to the large scale. So above at the left you can see the 25-liter system. This is a very compact system with LED lighting on the side, and the tube diameter is much smaller, is twice as small as the normal tube diameter that we use for the bigger reactors. And this is done so we can obtain much higher densities because light is less limiting, and then you can create much more inoculum for the larger system. This reactor is good to use as an inoculum in the seed train, but it is also a very good controllable reactor, so research can be done very well in this reactor to optimize productivities, for example. And to the right of that you can see Eugene in front of a 275-liter reactor, also with LED lighting. This is mostly also used for pilot scale and for research activities, but you can reach quite a good amounts of biomass, and this is more representative for the bigger scale system because of the tube diameter, which is the same. And below you can see a 925-liter reactor, which is outside. Our systems can be both placed inside and outside, and we can provide you with LED lights, extra or without. It's all possible. And the big system of 40,000 liter is installed inside a greenhouse, so we can either grow indoor, outdoors, or in greenhouses. Our reactor. Here you see the vertical or the horizontal reactor, which is installed in the Netherlands last year. And since 2012, Lgem has already installed over 80 projects in different places in the world, and it really shows that the technology is proven. And now with the combination with Synalgae, we can also provide a turnkey large-scale project. So to be using our proven technology, and now even in a large scale. We have installed. Created the algae hub in the Netherlands, where a demonstration scale microalgae production facility is located in the Kwakel, close to Schiphol. And this is our demonstration facility where we can prove and show that our large-scale technology is working, and also where we've learned a lot already, especially in in software and automation to connect both up and downstream to our reactors. So we are doing it ourselves, and here you can see 3 different PBRs containing up to about, varying, but about 10 cubic meters of culture volume, and we are growing spirulina. Here the green color you see is from the algae spirulina, and they have been inoculated in October last year, and they are still running without having to empty them once even. So we are harvesting weekly in these systems and keep on growing. So it's very robust and very efficient to work with these systems. And what are we doing in the algae hub, as we call it? We are getting experience for growing microalgae, different species of microalgae. We are growing in our systems to get experience, to get data. How fast can the algae really grow? And by getting these data, and what do they need for their optimal growth? By getting this data, we can validate business models for clients. We also rent out our reactors to clients if they want to get acquainted with a specific species, or if they want to validate their business model by real data, because we can create real data on a real scale. We can also produce biomass for different reasons. We have a capacity now for up to 3 to 4 tons of dry mass per year, and by getting this biomass, we can work on product market application development, and we can provide research projects with biomass. And within the facility, we can also train clients if they buy a system from us. Clients can send their employees to be trained in our facility, so then they can have a head start when starting in their own production. And of course, we are continuously optimizing the production with different algae and seeing what light does and how much light and how intense and how long, and which media is best, and temperature experiments. We can do a lot of experiments to optimize production in our facilities. And we have a lab. As you see, we could go from lab scale up to the demonstration scale. Now I would like to share with you some results we have obtained in our system in the algae hub. And here 3 pictures are shown of the different types of reactors that we have. In the top picture you can see a just inoculated reactor with Nannochloropsis. The color is not that green yet, but here we are cultivating Nannochloropsis. And on the bottom one, the brownish one, is a 275 liter reactor in an indoor situation where the room is climate controlled, and we use LED lighting. We are growing isochrysis for the aquaculture industry. And at the right, it's a picture, a closed up picture of the big system where spirulina is growing. Here results are shown from several species that have been cultured in Lgem photobioreactors. Most of them we have cultured ourselves in our system in the Netherlands, but also some have been obtained by clients from us in other places, like for example Tetraselmis in the University of Bergen in Norway. And you can see that we can obtain different maximum dry weights for different species, ranging from 4 to 12 grams per liter. And different productivities are also reached from 0.3 grams per liter per day up to even 0.9 grams per liter per day. And operating conditions, of course, are always dependent and will vary the maximum dry weight. We have, for example, mostly tried to reach semi-continuous cultivation by harvesting 30 up to 50% of the volume every other day or even every day, and then we want to stay in a certain dry weight where maximum productivity is reached. You can see that we have reached much higher productivities than Marcella just showed you, and I think I can explain why that is, because I have the feeling that maybe the algae in Marcella's reactor are light limited. They are only grown on natural sunlight, and there is no, to my knowledge, LED lighting available extra. And I think the the results could even be getting better if light is improved on her reactor. And as you see, we have obtained quite some high productivities with different types of species in our reactor. So just to conclude, I think Lgem photobioreactors are very, very suitable for phototrophic microalgae growth, and many different species can be grown in our system. Even up to the vulnerable species can be grown in our system because we can only operate it using air circulation, so there is no liquid pump damaging the cells. And Lgem technology is now fully automated and fully connected with up and downstream also, so it's easy to operate. And the algae hub is at your disposal to test, validate, and learn more about algae cultivation. So thank you very much, and if you have any questions, don't hesitate to contact me. Here you can see my contact details, and you can also always go to the website. But and I'm now open for your questions. Thank you very much.
Okay, thank you very much, Marieke. And now I would like to thank you all for the questions what you asked. And now I will just ask this question first to Marcella, and we'll get her answers. And after that, for Marieke. So please be with us. Thank you. So first question for Marcella was from Florian Delroux, asking, thanks for interesting talk. Marcella, when you say an inoculum, you mean digestate dilution? And also, why diluting the digestate and not increasing the retention time, use of water means? Thank you.
Yeah, thank you, Florian, for the question. So when I say inoculum, is actually the amount of algae cells that we're going to put in the system. So right now we're using 20% of the volume. So we have a 500 liter reactor. And this means that 20% of this volume in the beginning is added with a rich culture in algae cells. But if we increase, so if you heard Marieke's presentation, she said that they actually do a semi-continuous operation, that they harvest. They actually use inoculum of about 50 to 70%. So they harvest 30% of the volume, and then the rest stays there. So this means a 70% inoculum. So that's what we are aiming. If we have a more dense cultivation, you will have a much higher productivity. So right now we are using quite a low density cultures, and that's why one of the reasons that our productivity is low. I completely agree the light limitation is an issue as well. So we just installed LED lights, just getting the hook from Marieke's presentation, and we are seeing already increased productivities. So inoculum means, so it's the amount of initial volume of algae cells that you put in the system.
Okay.
And for the dilution of the digestate, so as I explained, you have to dilute. You cannot use strong digestate. It will just kill off the cells, mostly because of ammonium toxicity. So if ammonia goes higher than 100 milligrams per liter, or okay, a little bit higher depending on the cells, it becomes really toxic to the cells and it kills off the entire culture. So we have to keep the ammonium levels to below 100 milligrams per liter. And this means operating at around 2% digestate concentration, depending on the initial ammonium concentration in the digestate. So that's why we have this limitation, and we have to use very diluted system.
Thank you, Marcella. I hope Florian is happy with the answer. So I have another question, a little bit general, a global question from Solène, and she's asking about digestate valorization. It's a bit off topic, and sorry for that. Spreading microalgae instead of digestate in agriculture decrease eutrophication risk because nutrients are locked in algal cells, but are nutrients less available for plant because of that? Do you?
Okay. Yes, I know, because yeah, luckily I work in a biofertilizer lab, so I am equipped to answer this question. So indeed, that's a good remark. Yes. So you have to couple so you have to first evaluate what is the nutrient release rate of the algal fertilizer, and you have to match this to the plant's needs. So it may be that as a start, you need to put as well some mineral fertilizer or some digestate where the nutrients are more directly available for the plant to start to grow. But then you have to apply much less of these already available nutrients just to sustain that initial growth. And then probably the plant will uptake them so fast that they will not be available there to really cause purification. And then the rest would be slowly released by the algae. So it might be that every growth cycle, you need to reapply some of these more available nutrients in a mineral form or as organic form. But the advantage of the algae would be to reduce the amount of this ready available nutrients that you need to apply. And then it would really slowly release the nutrients during plant growth. So while the plant still needs nutrients, it will slowly release it.
Right, very interesting, Marcella. Learning myself loads, thank you. Another question coming to you from Yelise Bremont, sorry if I pronounce it not really right. So according to you in the paper filtration, solution scalable? Yeah, that's it, sorry.
Yes, so we are using a very small system because we have a 2,000 liter reactor at the moment, so it doesn't make sense to have a really full scale operation system. However, this paper filtration is used already in anaerobic digestion sector, and it consists of, it's not a bag as I showed in the picture, it's a continuous layer of filter. And it can be automated. So what happens, you have the filter here, so the digestate is just dropping. And when the flux at the bottom part of the filter is greatly reduced, the paper will just, it's actually a cloth, it will just move to the side and then it starts a new filtration system. So it's quite scalable, easy to operate. The only downside, if I'm being honest, is the amount of waste that's being generated because this filter, it's it's not easily. So the bag filter we can clean quite effectively. I don't know how this continuous system is easily cleaned, but our idea would be to try to use some biodegradable cloth or something like that when scaling up. So we can actually feed, well, the idea would be to feed this filter, this used filter to the anaerobic digestion system and then generate more biogas, more digestate and close the loop. That would be the ideal solution. So we weren't able to evaluate this in the project.
Okay, thank you, Marcella. I think so that's it. If you listen our webinar and recording, please put your question in the comment box below of this video on our YouTube channel. We will contact Marcella for asking questions again. And lots of people thank you for the nice presentation and really informative session. So thank you, Marcella. Now I would like to invite Marieke to answer the question, please. So
yes.
Hi, Marieke.
Hi, you can hear me.
Yeah, we can hear you. So first question is coming from Yelise again. So, and asking, does Lgem offer or recommend specific downstream solution for microalgae recovery? Thank you.
Yeah, thanks for the question. We have, depending also on the species, because some species are very vulnerable and others are not, and then spirulina has large chains, so we have different technologies and work together with different partners in this case. We normally do use a filtration unit, ultrafiltration, to be able to to concentrate the cells, to get like rid of the easy water, and then this makes it also possible to recirculate the water and to use the nutrients that are still present in the water. And then after that, the thickened stream is not yet a paste, so then we use a centrifuge. We now have a centrifuge from GEA, but we are also working with Evodos, depending on the on the vulnerability of the cells. We choose the right technology. So in this case, we always work together with partners to provide the right harvesting technology.
All right, thank you. Another question from Pascal from GPR asking, could you give some information about the way the light dark cycle is obtained?
Yeah, I think, yeah, we have lighting from the sides, from above the reactor, depending also on the geometry of the reactor. And the thing is, due to the wave that we have in the system, the mixing is very efficient actually. So the cells do go, like come to the surface and go back into the to the depth of the reactor, so to say, or of the liquid. So that means then we get very fast light dark cycling in the system, and the cells can then use very efficiently the light that is being obtained when they are exposed to the light.
Okay.
I hope that gives the answer.
Yeah. Okay. Another question is about from Sarah Morena, and she's asking, would it possible to stack the PBR system models or make them taller, for example, to fit more volume in a given area and reduce the land footprint?
Yes, indeed. It's a very good question, and this also depends on how you want to grow algae, because we have two approaches. We think that a horizontal reactor, so actually less volume per square meter, is better if you want to use sunlight, because then you use more efficiently the sunlight and less LED lighting or no LED lighting is necessary. But if you want to grow indoors, or if you do want to use LED lighting extra, then it's better to go stacked. So we have two types of reactors. One is indeed stacked, and then the one we now have is it's a stacked reactor, so horizontal layers on top of each other. The one we have now is using both LED and sunlight, but we are also providing systems for indoor, and then we will even go much higher. So because then of course your footprint is lower, and you can put the lights as you like. So so indeed that is possible. Yeah.
Okay. Super, thanks. Another question about Haematococcus pluvialis culture. So you give a productivity numbers in the green stage for the results, what you've shown. So I don't know, can you just comment on it, please?
Yeah, that is true indeed, because it's a two-phase system, and then the green stage is is the growth phase, so to say. So the number I've showed was for the green stage indeed. Yeah.
Okay. Super, thanks. Another from Alexandra Eskos. She's asking about the material what you use for your PBR and why you choose this. Very good question.
Yeah, I actually had a slide in there, but my presentation was too long, so I took it out. But it's a good question.
Yeah.
We have glass tubes, and actually we started in the first systems we had PVC tubes, but we experienced that the color and the was changing, actually visibly changing, and the light throughput was very low. So we've in 2006 we made the change to glass tubes, and we actually noticed that the light throughput is perfect. Cleanability is also very good, and biofilm forming is lower than we saw with the PVC tubes. So and actually it lasts very long. So the lifetime of a glass tube is very high. So those are all reasonings for glass.
All right. Okay. Thanks. And another question from Jay Silam asking, what is the best way to detect or monitor biological contaminants in the Lgem system? And
yeah, thanks for the question. This is actually quite a difficult one, and we are it's always a thing that you want to know what's happening in your system. And actually the way we now monitor it is we take samples daily, and we monitor growth, of course, but we also always visually look under the microscope to see if it's still clean enough, and if contaminants are growing more or less, or if things are changing. So microscopy is in this case the method. I do have to say that we are now starting a collaboration with NEO, an institute from the Wageningen University, to get more in-depth knowledge about possible contaminants present, and also to get to know more knowledge when it starts growing more, or what we need to do to prevent it. And this will be more based on DNA technology to get more in-depth knowledge, because now what you see, if there is a contamination, and once you start seeing it can be too late already, because then it started growing already a lot. So we really take much care with when we inoculate. So the seed train really needs to be clean before putting it in, and then afterwards we try not to open the system at all, and we always have filters to get it in. So we keep it as clean as possible while growing. And also what is important is to keep the culture as optimal for your species of algae, because then contaminants won't get any chance.
Yeah, good plan. Yeah, I agree. And very last two questions actually from Vadivasa Manikian. How this technology can produce large volume of biomass and it's scalable and cost-effective way, I can imagine. So
the thing is, actually we work in a modular way. So we have systems. Our largest system is 40 cubic meters, and that is really a long tubes and all connected together, and we work in a modular way. So our way of scaling is to put more of those systems besides each other, and the only thing we do connect is that we have the up and downstream of all reactors connected. So you can use one downstream process stream to harvest your algae, but the reactors themselves are all modular, so you can also inoculate just one, and if something goes wrong, it's just one reactor that is a problem. So that is actually an easy way of scaling, and and as you saw, the productivities are quite high, so that means we can create high volumes of biomass with many systems then.
Yeah. And very last question. So can you explain about usage of vertical plastic bag, PBRs? I think it's kind of low cost technology.
Yeah. I'm not so. We use actually plastic bags, but just in our seed train, so on the liter scale to get inoculum for our next step. But we see that mostly the vertical bags, like the sea caps that is used in aquaculture systems. The thing is there that the productivities are not that high, and the light path is mostly very wide, so densities that you can reach are quite low. So you need more volume to actually operate. But especially in aquaculture systems, it's not such a problem because they continuously dilute, and it just keeps on growing in those systems. So it's possible to do it, but we think in our systems we can get much higher productivity. So in the end, the footprint is lower, and we don't have to throw away bags because the system just keeps on working, and it's not disposable. So we are more in favor of non-disposable material, which makes, of course, the investment costs higher, but actually operational costs in the end are not don't really have to be higher.
Yeah,
final cost
absolutely.
price. Yeah.
Super. Thank you very much, Marieke. Lots of people thank you very much for a fantastic presentation and really informative talk as well.
Thank you all.
Thank you. But I just would like to tell the people who will be listening our talk and replay from YouTube channel, if you have any question to Marieke, please let them put them in the comment box, and we will contact Marieke for the right answers. So thank you very much. I think our webinar come to the end. I just would like to basically ask you to save the date, because our next webinar will be on 8th of April from 2 to 3 p.m. of Central European time and 1 to 2 p.m. from UK time. And this webinar will be all about Brittany pilot site. It's another pilot site of ALG-AD project, and results will be presented from Luc Chauchat from CNRS, and also we'll have talk from the company called Biorea, talk about heterotrophic of growth of microalgae. I invite you all for this. And thank you very much all who came today to listen to our webinar and your participation, active participation today. And now I would like to invite you to fill in the opinion survey that will appear on the screen before you disconnect it. Thank you very much, and see you soon.